So now we have the we start with cyclohexanol, and then we oxidized it with a Jones oxidation to get cyclohexanone. So I'm looking at the NMRs at the moment. We can start here, why not? Clearly this was run on our instrument, and I took cyclohexanol straight out of the bottle. And on that day that I ran this, I'm pretty darn sure that the sample wasn't spinning great. So you can see how broad those peaks and absorptions are. But in any event, you can clearly see how you're going to get two sort of large lumps, integration of 2 and 6. So when you look on the ring, where are we? Cyclohexane systems, because of the chair configuration, you're going to have certain hydrogens sticking up and others down. And that OH, for instance, is going to be above the ring while the other hydrogen right here will be below. So long story short, at each of these positions, you're going to have a hydrogen that's up and one that's down. So this is not going to give you nice N+1 splitting. You're going to get, lumps of forest peaks. However, the hydrogen that's on this carbon, directly attached to the carbon that this oxygen is, that's going to be the signal arguably furthest that way. And that one will be talking to multiple next door neighbors above and below the ring, whereas the hydrogen on the oxygen should be sort of a single broad kind of thing. Now we can't officially know which is which, but I'm willing to bet that this is logically likely to be this hydrogen because it's splitting to so many other things. That's why it's spread out so much. See how this one, even though it looks like a singlet, it's still pretty tall. But you could confirm or deny which one of these two is which when you go on that SDBS website. You'll definitely know which one is which for cyclohexanol. It's a better reference spectrum than certainly this one would be. And then when you look here, you could arguably say, see the 2 hydrogens here and 2 here? So that's 4. The remaining 6 will be in the other peak. So that's why this lump, which is arguably worth 4, belongs to these 2 positions, and then this lump will integrate to be roughly 6. So that's out of the bottle cyclohexanol. The carbon spectrum, I mean, it makes pretty much sense. That's TMS at 0. The signal that's furthest down has to be the carbon that has oxygen directly on it. The next in line are these 2. Now by symmetry, the carbons, these 2 carbons are the same. So you're going to get a signal for that. Then you're going to see 2 carbons that are symmetrical and 1 that's not. Now the 2 that are symmetrical, you have double as many, so arguably it should be this taller one. The shorter one logically should be this one here because there's only one of them. The heights of the carbon peaks kind of show that one. SDBS website will probably have that for you. Now as far as the cyclohexanone, this spectrum is essentially a reference spectra because it comes straight out of the bottle. It's 100% pure, run on our instrument. So again, we definitely would expect that the 4 hydrogens at these 2 positions, some are up, some are below the ring. You're not going to get N+1 coupling. Something worth 4 should be slightly more left than these 3. And sure enough, you get a lump, looks ugly, should roughly be 4, and then the other will be the remaining 6, in which it is. That is cyclohexanone. And then when you look at the carbon from that right out of the jar, you see 1 peak past 200, which is obviously the carbonyl carbon. And then you can play this out. These 2 carbons will be between 0 and 77 is what we normally think of the alkane or sp3 carbon region. So out of that region from 0 to 77, these carbons closest to the electronegative carbonyl should be further left. Then you should have these 2 and then that one. But the heights of them will tell us. So this carbon has to be the 2 carbons closest to that. Next in line and tall one would arguably be that one, which it is. The shorter one belongs to that one. Now, what's interesting is here is actually, this was run at the University of Windsor on, I think, a 300 or 400 megahertz instrument. So this actually was my product from the reaction that we did. This is crude after rotovapping. Now, obviously on a 500 or 300 megahertz machine, you can see how much better separation you're going to get. Clearly, and I'm looking here, when you're looking at this one, you can see how you're definitely having some extra splitting here. This is confusing. When you look back at the cyclohexanone on ours, this is interesting. Do you see this blob right here? How it's at 2.3-ish? Let's go over and look at 2.3 over here. C2, 1, 2, 2.2-ish. See how you get it looks like a triplet, really. And then you see the other blob. Now see how that right there integrates to 4 hydrogens? And you see how these 2 blobs, 4 plus 2 is 6. So you go back over to here. The first blob at 2.2 was worth 4. This blob was worth 6. So clearly, this blob becomes resolved on a higher powered instrument, which is these 2 lumps right here, right? That is the other one we already pointed out. This singlet, by the way, now on this instrument is 2.02, so maybe the TMS for them was a little bit off that day, but that's acetone, R2.17. So that's acetone, clear as day. This triplet and that quartet is diethyl ether, which is very common, folks. So you guys can very well expect that most of you are going to see some evidence of diethyl ether and acetone. And because when you look at this one, and it wasn't ever integrated, but you can see there's a sizable amount. So when I look in the carbon, you can see the TMS peak at 77. That's your reference, right? And look at all these forested peaks. So you say, wait a minute, let me go to my reference spectrum. Pure cyclohexanone carbon only had 3 peaks. And the numbers, 42, 27-ish, 25. So I'm going to go over here, and I'm going to say, okay, 42, 27, 25-ish. So these 2 and that 42, this one, that one, and this one are my product. 1, 2, 3, 3 extra peaks. 2 of them are diethyl ether. 1 of them is acetone. I'm willing to bet acetone is probably the 30 peak. You could easily confirm that using SDBS. If that is acetone, there has to be another carbonyl peak, and sure enough, there is. Our product, cyclohexanone, is 209. So go over here. Now, again, on this day, they didn't set their reference quite great, so you're going to see these 2, and you're going to laugh at the numbers. You got 206.9s, 207 and 212. So which one is acetone and which one's our product? Here, not 100% sure, but you can clearly see how this is a typical thing you'll see at lower resolution. So that's the NMRs. Now we can look at the IRs. By now, this should be like a done deal. You've got alkane functional group and an alcohol. So you go over to your book and you look up under the alcohol section in Pavia, and primary alcohols, a 6-membered ring, the CO stretch should be 1050-ish, and that's usually pretty strong, and then 3640, 3630-ish for the OH stretch. Those are the 2 main things you're looking for an alcohol. So you go over here, and pretty obviously we know this is your OH stretch, the CO stretch, 1067. See that one right there? That's your CO stretch. All that's left is alkane. So clearly these right here, just to that side of 3000, is a carbon sp3 hybridized with a hydrogen on it stretching. You can see that clear as day, and I've noticed lately that many people have obviously not been going back, clear as day, to this book. Look at the, for instance, alcohols. Now let's look at example spectra. There's an example of an alcohol. You can see the OH stretch. Oh, and look at this. Look at this. Notice how throughout all Pavia, they literally will write a carbon that's sp3 hybridized with a hydrogen on it stretching. See how they write all of this? Folks, we're getting to the point that if all I see written on your IRs is CH stretch and you don't put the sp3 in there, we have a problem. And even better than that, I've even suggested you should circle and then use this arrow pointing to what you're writing. So going back over here, ideally you can circle this, put a little arrow saying sp3 carbon with a hydrogen stretch. STR is good enough. So folks, there's no excuse when you see how many reference spectra you have where the way he's labeling it is all over the place. So that makes sense. The only other thing you could, for this one, there's no aromatic, there's no carbon-carbon double bond. So obviously, this type of stuff right here has to be a carbon-hydrogen bend, an actual bend. Now, do you see how what he's done in his book in that region? Now, he's not necessarily circled anything. If you want to learn more about it, we can back the train up here to the alkane section and look at what they've done there. So let's back it up. When they had a pure alkane, it stands out like a sore thumb. They were actually able to mark which one was a CH2 bend or a CH3 bend. I am more than happy just saying it's a carbon-hydrogen bend, right? I'm okay with that, right? Now, as soon as you start throwing other functional groups in here, sometimes he'll label it, sometimes he doesn't, because even he's probably not 100% sure. Look at this one. This is an aromatic example section. Here is toluene, which absolutely does have a methyl group on it. But you can see how he didn't bother. See that one right there? Or potentially that one? Right in that 13 to 1400. See how he's got these three as being a C double bond C stretch, but he did not label those ones. It's a classic case, folks, where this region, nobody normally likes to label stuff in there unless they're absolutely sure. So anyway, your product. This is pretty much a done deal. There's your alkane, carbon sp3, hydrogen stretch. You have a carbonyl, so the only thing with a carbonyl functional group that you're ever going to label, yet again, you go to Pavia and you remind yourself what it is that you're looking for. And whether it is an aldehyde or even a ketone, everybody knows the classic carbonyl stretch is the big strong one right around the 1700 mark. And notice how if over there you see a spike, that's a CO stretch overtone. Each one of these spectra has it. Sometimes he labels it, sometimes he doesn't. But when you see that characteristic little spike, and let's flip the page, see what he has here. Ketones. He's doing it again here. There's that little overtone. He has this one, obviously, he has a double bond that's close to it. That's why that one looks that way. This one has a strong carbonyl, but there's that spike of CO overtone. That basically handles it, folks, for that. So I think we're good.